So the last thing we did is we showed that any UFD is integrally closed. And I think that you can take what we did and massage it just a little bit to get what's on your homework about every UFD being completely integrally closed. Let me give you this lemma that's it's kind of silly. When you look at the proof, it's almost, wow, not too much to it, but it actually is quite useful, and we'll see it come up. Lemma 15.1 10. Let R and T be domains. And U a unit in T. So U is something in the larger ring that's a unit. Then U inverse is integral over R. If and only if U inverse is in R unit. Okay. This is important in the sense that in a certain sense, it shows that although in an integral extension you can have new units, you can't turn things in the base ring into units upstairs if the extension is integral. And this one just basically kind of follows your nose. Suppose U inverse is integral. So this means that U to the minus N plus R N minus 1, U is N plus 1. Right, plus R N minus 2, U to the minus N plus 2, plus R1 U inverse plus R0, 0. Here R is and R. So this is just the equation of integrality, right? Now, what I want to do now, let's see, I want U inverse and RU. So I'm going to multiply by U to the N minus 1. So I'm going to multiply both sides of this equation by U to the N minus 1, giving me U inverse plus R N minus 1 plus R N minus 2 U plus R1 U to the N minus 2 plus R0 U to the N minus 1 is 0. And therefore, U inverse is equal to minus minus, it's crap. Right. So U inverse is a linear combination of the powers of U, our linear combinations, so therefore. And the other direction is almost the same. Now suppose U inverse is in RU. So U inverse is equal to R0 plus R1U plus R N minus 1 U N minus 1. So there. Any questions? Yes.
I missed the, like, you have the arrow there for here, say the other.
Yeah, you just multiply both sides of this equation by U N minus 1.
Oh, okay, sure.
Okay. Any questions on that? Okay. Lemma 15.11. We're going to use this after a bit as well. an arbitrary intersection of integrally closed domains is integrally closed. This is cool. If I intersect integrally closed domains, I get an integrally closed domain. So let me do it this way. Let Ri be a family of integrally closed domains. Let's say all contained in some large array. Right, I don't want to intersect like Z mod 2 and Z mod 3, right? Then is integral closed. Okay, proof. Let R equal, for convenience notation, I'm just going to call that intersection R. And let suppose omega is in K, the quotient field of R, and omega is integral over R. So take something omega in the quotient field of R that's integral over R. So it's root some polynomial. Notice that since R is in Ri, K is in Ki, the quotient field of Ri. So R is contained in each of these Ri's, so the quotient field of R is contained in the quotient field of all of these. So omega is in Ki and is integral over Ri. Right? Because in fact, omega is the root of some polynomial coefficients in R, and of course those coefficients are all in Ri, right? So hence omega is in Ri because each one of those Ri's is integrally closed for all I. Therefore, omega is in R. And so R is integrally closed. Okay. Any questions? Now, for the moment, it will appear as if I'm having a stroke because I've been talking about integrality and this kind of thing, integrally closed. And now, all of a sudden, I'm going to talk about something called a valuation domain. Looks like I'm doing something different. However, it is going to turn out, big theorem, that the valuation domains are key in understanding integrality. In fact, it's amazing how key they are. I'm going to start, unlike what I do with the homework, I'm going to actually start with what the word valuation means. What a valuation is it is a function from the field into, sometimes you think of this, well, actually, into a totally ordered abelian group with some properties. So, definition. Let's let K be a field. A valuation on K is a function I'll call it function V from K star, and by K star, I mean just the non-zero elements of K. The valuation may not be defined on zero. To whatever this guy is, gamma, where gamma is a totally ordered so what it is it's a function that goes from the non-zero elements of the field into this totally ordered abelian group. The totally ordered abelian group, the idea is it's totally ordered. So now the valuation gives a way to compare things in the field because based on what its output is here. Because the field may be a mess, but this valuation gives you a way to organize these things and measure it. Because if you have two elements of K, say X and Y, then their elements over here in the totally ordered abelian group are comparable. Either V of X is bigger than V of Y or vice versa, right? Because it's totally ordered, right? I want my valuation to be nice in the following sense. Such that, one, valuation of AB is value of A plus the value of B. So it's like a logarithm in a certain sense. And two, value of A plus B is greater than or equal to the minimum of the two values. Here, A, B, A plus B are non-zero. Because I want to be in stay in the domain. And equality occurs if and the valuation, the value of a sum of two things is the minimum of the two values. In fact, it's equal to the min if the value of A and the value of B are different. And if the value of A and the value of B are the same, then, well, this could even be undefined, right? Because the value of A minus B is undefined. But if they're the same, then it could be bigger. In some cases, you might have equality depending on the specific elements A and B, but in general. So let me give you an example or two. Example. All right, look at a power series ring of a field in one variable, right? Any non-zero element of f power x is a form any non-zero element and n is greater than or equal to. Any non-zero element of the power series ring over a field is of this form. Everybody agree with that? Because just look at the power series. Basically, n is the smallest appearing degree of a term in the power series. Are you okay with that? Pull that xn out. Keep in mind that xn could be zero, right? It could start with a constant. Pull that out, and what you've got left over is a unit. because A n is not zero, and you're over the field. Everybody agree with that? So any element, if alpha is in f power x, but it's not zero, then alpha is equal to x to the n times the unit. Do I agree with that? So any element in the quotient field non-zero is of form x to the k u, where k is in z, u is in the units of f power x. Right, because anything in the quotient field is an x to the nu over x to the mu prime. So that still gives you a unit in f power x. But now the exponent of the x can be either positive or negative. Everybody agree with that? Can anybody tell me what the good valuation be on this? What's a natural way to shove this into a totally ordered billiard group? What totally ordered billiard group might I pick? Z. That's one of the easiest examples of valuation. There's also the trivial valuation, right? That is, you can take a field and you can send every send every non-zero element to one. That's also a valuation, right? It's sometimes called trivial. Yes.
How does this differ from like a Euclidean function?
Well, actually, this Euclidean function is too good. It's different because you're not gonna. So for this one, first of all, this is defined on the entire quotient field and not just 3 itself. So that's one thing. Second of all, this particular one, because of the fact you're going into Z, this f power x is in fact a Euclidean domain. But it's not the best example because what happens is, given any two elements in a Euclidean domain, you can divide one by the other. If the value of what you're dividing into the other one is a smaller value, then the remainder is 0. If the value of what you're dividing is strictly greater than what you're dividing into, then the quotient is 0 and the remainder is what you're dividing into. Right, so. Another example, yes.
How did you get K?
Just by reading the exponent.
Oh,
Right, that's the way the function's going to work. Another example is take we can define value P from Q into Z as well. And here's what I'm going to do. If alpha is in Q, but it's not 0, then alpha can be written as P to the K times U, where U is equal to A over B, A, B, and Z, GCD of AB equals 1, and P does not divide A, P does not divide B. So in other words, if you take alpha as a fraction of two integers, pull all the powers of P out of the top you can, all the powers of P out of the bottom you can, reconcile that as P to the K, could be positive or negative. And what you've got left over, you can assume is a reduced fraction, and there's no P dividing either one of them. VP of P to the K U is K. It's essentially the same as this. This is called the p-adic valuation on the rationals. There is a p-adic valuation for every prime. But valuation domains can be, oh, so more exotic. You might think of how to construct one that has value group Z instead of that thing will be a huge mess. You can get one that's a value group, direct sum of Z and Z lexicographically. You can do all kinds of crazy crap. Proposition 15.2.2. Let's let V be an integral domain of quotient field K. Domain with quotient field K. The following are equivalent. Number one, for all non-zero A, B, and V, either A divides B or B divides A. By the way, this is the first definition I ever saw of a valuation domain. What does it mean to be a valuation domain? It means any non-zero element, any pair of non-zero elements A and B, one of them divides the other. And I thought, how stupid is this, right? I mean, an obvious example of a domain with this property is a field, right? Every field's a valuation domain, and I remember thinking, this has got to be pretty close to being a field, right? Right? Like the on the daily show. Yeah. No, not right at all. These things can be really crazy. Two, for all U in K star, that is the quotient field, either U or U inverse is in V. So take anything in the quotient field, either it's already in V or its reciprocal is, one of the two, sometimes both. Three, and this is why I define valuation. V is the collection of X and K such that Vx is greater than or equal to 0, union 0, for some valuation V on K. Definition. So I'm going to throw this in. Any domain that satisfies one, hence all of these things, is called a valuation domain. The equivalence of the first two is not too bad. So I'll just do one of these directions here. One implies two. So you have for every non-zero A and B, either A divides B or B divides A, right? So let U be in K star. So U is equal to A over B for some A and B in non-zero elements V, right? Note if B divides A, then U equals A over B is in B, and if A divides B, then U inverse, which is B over A. Yes,
What is K star?
non-zero elements of K. Yeah, when I use that star, that's what I mean by that. It's a little bit trickier to show. Well, let me do 3 implies. Right, 3 implies 2. So suppose that V is this, it's the non-negative elements of, oh, by the way, this valuation goes into a totally ordered abelian group. 0 means the identity of this group, and what it means, since it's totally ordered, this is well-defined concept. Suppose that we have that V, we have some valuation on K, and V is the set of non-negative elements, union the 0 element. I'll let U be in K star. I want to show you the U or its inverses in there. Okay. Notice that U inverse equals 1, which is in B. Perhaps I should show why that's true. Notice that the valuation of 1 equals the valuation of 1 times 1, which is the valuation of 1 plus the valuation of 1. Right. So since this is a totally ordered abelian group, I actually don't even need that at this point. So what you have is valuation 1 equals valuation 1 plus valuation 1. Subtract this from both sides. You get the valuation of 1 is 0. Therefore, since the value of 1 is 0, then by definition 1 is in V. Right? Because it's got a non-negative value. Suppose value of U and value of U inverse are both less than 0, then value of U plus value of U inverse is also less than 0. Therefore, value of U inverse, value 1 equals 0 is less than 0, contradiction. So, value of U or value of U inverse, one of these animals at least has to be greater than or equal to 0. Therefore, U or U inverse is empty. I'm not going to go over this because I want to get on to some other stuff. How do these properties get you that value? You might think about that, and if you struggle to get it out, I'll show you how you can use this property to actually build the valuation that you need. Okay, but here's the first bit. So I'm going to call this proposition 15.2.3. Any valuation domain is integrally closed. And this is one of the things that makes valuation domains just so important. They're always integrally closed. You will notice from the homework that valuation domains are, well, they're almost never, they can be, but they're almost never completely integrally closed, but they're always integrally. And I'm gonna use my little limit here. Let's suppose that V be a valuation domain. And alpha in K, quotient field V, integral. Integral of V. If alpha is in V, then no. So we assume alpha is not in V. So let's assume that alpha is not in V. Well, V is a valuation of it. Alpha inverse, right? Because when alpha is not, you've got no choice but to come to the conclusion that alpha inverse must be in V. But since alpha is integral of V, alpha is in V alpha inverse. This is me using that lemma from earlier today in class, but I role reverse. Instead of saying U inverse is in V U, I say U is in V U inverse, right? It's symmetric. And this is equal to V, right? Because alpha inverse is already in V. And this is the desired contradiction. So V is integral closed. Okay. Any questions on that? Okay, so that's one big thing. Valuation domains always integrally closed. And in fact, we're going to see later that valuation domains are basically the building blocks, integrality. But here are some more properties. Here's some more cool properties of valuation domains. 15.2.4. Let be the evaluation domain. Then V enjoys the following properties. Number one, the ideals of V are, anybody want to guess? This is another just fantastic fact about valuation domains. And you hardly ever see this. The ideals of V are linearly ordered. So if I give you any two ideals in the valuation domain, one of them contains the other. That's pretty rad. So any two ideals are common. Number two, what else? Oh, this follows from this. V is quasi-local. Right? Remember, what it means to be quasi-local is it's got one and only one maximal ideal. Well, if you think about the previous statement, if you believe that, you've got no choice but to conclude this, because suppose you have two maximal ideals, M and N. One of them contains the other, so you can only have one. Number three, any radical ideal of V is prime. I know you all saw this. Some of you may or may not have seen this. I know you did. It depends on people's emphasis. Does anybody remember that the radical of an ideal is the intersection of the primes that contain it? Right, so to compute the radical of an ideal, just take all the prime ideals that contain and intersect it. Well, the primes that contain any ideal, if it's radical, it's an intersection of primes. Those primes are linearly ordered, so it has to be prime. 4. This is another one. Any finitely generated ideal of B is, do my own guess? Given the property that any two elements, one of them divides the other, you should be able to figure this out in principle.
Is it principle?
Take an ideal that's generated by two elements, A and B. One of those elements divides the other. And whichever one divides the other one, the other generator is redundant. Now go by induction, right? So any finite generated ideal. And in fact, if you put together 2 and 4, this characterizes valuation domains. Valuation domains, another way to think about it, are B is a valuation domain if and only if it's got properties 2 and 4. So that is to say, if it's a quasi-local Bezier domain, how many of you have ever heard Bezier domain? Anybody ever heard that terminology before? It means all finitely generated ideals are principal. So if you have a Noetherian Bezier domain, it is a
Generate domain.
So if you have a Noetherian domain, every ideal is finitely generated. And now you throw in Bezier, which means all finitely generated ideals are principal.
Yeah.
It's PID, right? So a Bezier domain is an analog of PID in the non-Noetherian case, right? If you're looking for a fun example of this, look at the ring of entire functions on the complex plane. This is a Bezier domain that is very far from being a PID and has many strange properties. Okay. So I will record this. But I've got this as an exercise in homework, and it's a neat little exercise to show the equivalence of these. Proposition 1526. B is a valuation domain. If and only if B is a quasi-local Bezier. So, like I said, I'll leave that as an exercise. Oh, yeah, well. Okay. Any questions so far? I'm going to throw in another lemma that always to me kind of reminded me of that integrality thing I did a little bit earlier, and it will prove very interesting in kind of the centerpiece theorem I'm going to do. Pretty soon now. And this is almost kind of like high school alpha in a certain sense. I mean, obviously it's much more complicated than this. Lemma. So this is a big lemma 15.27. Let's let R inside T be domains. I and R a proper ideal, and U a unit in T. Then I survives in, and I'll take it. So before we go getting up under the hood of this one, let me tell you what I mean by survives. If I and R is an ideal and R inside T is an extension of rings. So you could do this in a much more general sense. I'm usually assuming that these are domains. Doesn't have to be. We say I survives in T if IT is strictly contained. Okay, so what do I mean by this? So if I is a proper ideal of R, we say it survives in T if it retains its proper status, if it doesn't blow up to the whole rank, right? So for example, right, 2Z survives in CX, right? Because the ideal generated by 2 up here, this is just all polynomials with all even coefficients. There's no way you're getting a 1 out of that, right? So it survives. 2Z in Z does not survive in Q, right? Because in fact, the only ideal in Q, the only proper ideal in Q is 0, right? And so when you lift 2Z up to Q, all of a sudden there's 2 hanging around, think it's going to be cool, make an ideal, and along comes 1/2, and you got everything, right? So this doesn't survive. If you lift 2Z up to Q, it's everything. Or A, B, C, and 3 does not divide B. This is the set of rational numbers where the where the denominator is not divisible by 3. Notice that this thing contains 1/2. So if you lift 2Z up to this ring, you've got that 1/2 again, that turns it into 1. So now I've given you simple examples because these are principal ideals, and it can be more complicated than this, but that's kind of the gist of it. But this is kind of an amazing theorem, I think, because if you have a proper ideal in R, and U is a unit here, then I survives either an RU or RU inverse. In one of those two extensions, or both, but in at least one of these, I has to remain a proper ideal. Why is this true? True. Suppose not. We'll say that I blows up. This is actually the terminology. Blows up to the whole ring in both RQ and RU inverse. And we're going to do a minimality contradiction. So actually, I don't think I'm going to be able to get through all of this. So let me just kind of set it up and leave you with something to think about, and you can finish it off next. So let's suppose that this blows up in both RU and RU inverse. This means that the ideal IRU and RU inverse equals RU inverse, right? So in particular, what that means is in both of these separate rings, you've got to be able to get a 1 here in this ideal. So you get a couple of equations that look like this. The first in RU, let's say A0 plus A1U plus A2U squared plus, I'm going to keep my notation here, go to the other end first. ANUN equals 1. So this is what a typical element of IRU looks like, because IR, anything times IR is NI with AI. And B0 plus B1 U inverse plus B2 U minus 2 plus BM U minus M is equal to 1. And here the BI's are also an I. So you have to have two equations like this. Let's assume that N is greater than or equal to M and is minimal with respect to the length of that equation. Okay. What we're going to do, yeah. Okay, so what I'm going to do is I'm going to assume that one of these is less than or equal to the other, and I'm going to assume that in terms of U, this N is minimal, right? Now, what I'm going to do is I'm going to massage these equations, and I'm going to contradict the minimality of N. I'm going to find a smaller equation that works it, using the fact that these are negative powers, positive powers, and so forth. So you might think about how that's done, and we'll spoil it for you tomorrow. Well, Friday. Okay, any questions? Let me remind you that I was supposed to be out of the office today from 11 to 12. That has been shifted to Friday. I will be out from 11 to 12 Friday, but I've got full office hours today. Don't forget the math in Saturday, and we have a review session on Wednesday next at 5. Okay, question.